Okay, we're live. All right, Bio 375 class, we're going to go through the group problems really quick and hopefully be able to explain them so that you and ourselves understand them better. So question 1, all these questions essentially follow the same format except for question 5. So we perform a test cross between a heterozygous and a homozygous recessive, and we get these observed progeny right there. And we need to determine the allele arrangement in the heterozygous parent, determine the gene order of the 3 linked genes, and then construct a linkage map showing the map distances between the 3 genes, and then calculate an interference value. So with question number 1, for A, we have these 3 different phenotypes or 3 different genes. There's the mahogany gene, the agouti, and the ragged. And those are all the recessive versions of the genes. And so to determine the allele arrangement in the heterozygous parent, you look at the values that are highest. And for this case, it's 76 and 69. And so on the top, you put agouti, which is the recessive. You put the wild type, which is RG plus. And then mahogany, that's the recessive, so you put that on the bottom. And then for the 69 value, there's the wild type right there. There's ragged, and then another wild type. And so that is simply how you do the allele arrangement. And then for B, this involves looking at the double crossover events. And you do that by looking at the progeny, the least value. And in this case, it's 1 and 1. It's agouti, ragged, and wild type. And then wild type, and mahogany. And so you put those values down, and then you kind of just have to check, like, I don't know an easy way to do it, but you kind of have to just check for what the gene order is to determine which one will help you in these values. I don't know how to explain it very well, but essentially in the end, after you write out the different possible gene orders that there could be, like right there, we find that the correct gene order is this first one that we have, which is wild type, agouti, mahogany, and then ragged, wild type. And then, so using this gene order, we can construct a linkage map. And that is done by taking the 2 different possibilities for when crossing over takes place. And so you take the top one and these bottom 2 and circle them, and then the bottom one and these top 2 and circle them. And then you find the number of observed offspring from these 2 phenotypes. So this one is all 3 wild type, and there happen to be 16 of those. And then this one is all 3 recessive, and there happen to be 18 of those. And you take that value, do 18 plus 16, plus the number of double crossover events, which is 2, and then you divide that by the total number of offspring, which was 206, and multiply by 100. And that tells us that it's 17.48 map units between RG plus the ragged and between ragged and agouti, these first 2. And then you do the same thing with the next one, except you do the top 2 and bottom 1, and then the bottom 2 and top 1, and find the number of offspring in those phenotypes. And that's just 13 plus 12, and you still add the double crossover observed, which was 2 over 206 times 100, and you get 13.11 map units, and that's the distance between agouti and mahogany. And then you calculate your interference value, and that is done by simply taking these map units, which tells us how far apart they are on the chromosome, these linked genes, and you take both of them and turn them back into their original form without multiplying by 100. And so in this case, it would be 0.1311 and 0.1748. And you multiply those 2, by 206, which is the total number of offspring, and you get 4.72. So that's how many are expected. You expect to have 4.72 double crossover events, but there's only 2 observed. And so you do 2 divided by the number, so 2 observed divided by the number expected, and then multiply that by 100, and you get 42.4% interference. So it's kind of a mouthful, but there's question 1, and now I'm going to switch it over to Haley.
Okay, so question 2 goes the same way as question 1. It's just different genes. So let's see, we're talking about Drosophila eyes, and we're talking about scute bristles, sable bodies, and vermilion eyes. I use S, C, S, and V. Plus N is going to be the wild type. So for A, the largest ones are right here. The parental phenotypes. And so for B, so we start B by finding the lowest numbers. They're going to be the SC plus, S plus, V plus. 3 of them are the wild type, and that gives us 14. And then SC, S, and V is all of the traits, gives us 10. So the way that I try to do the recombination is that I try to switch the first and second alleles. And if that doesn't work, then I switch the second and third alleles. We found out that the right order, the double crossovers, is going to be V, SC, and then S. So for C, we take that, the V, SC plus S over the V plus SC, S plus, and then we cross the first allele with the bottom, second, and third alleles, and then the first allele on the bottom with the top, second, and third alleles. And that gives us VSC, which is 46 of the offspring, SC plus S, which is 30 of the offspring. Goes to the number of double crossovers, which is 24. That gives us 100 over 1,000. And we multiply that by 100, we get 10 map units. For the second one, we're going to take the first 2 alleles from the top, and we're going to put them with the third allele on the bottom. And then we're going to take the bottom 2 first alleles and put it with the third allele on the top. The VSC plus, S plus, which is 156 offspring, and the V plus SCS, which gives us 150. So when we add those all up, put them over 1,000 and multiply it by 100, that gives us 33 map units. For D, we just multiply those numbers that we got, the 0.33 times the 0.1, 0.033. Multiply that by the amount of how many offspring there were, we get 33 expected. When we put that, when we divide the number of double crossovers, which was 24, by the 33 expected, we get 72.7% interference. And that's number 2.
Perfect. Okay. And then for question number 3, this one was a doozy, but good, because it was good. Okay, so we had all of these different phenotypes observed in this test cross for glassy eyes, coal body, and a striped thorax. And so for this one, there was 2 phenotypes that didn't come up, and so we just assumed that they were 0, that they didn't happen. Okay, sounds good.
I'll be back in an hour. Will you still be here?
Yes. Sorry. Okay, and then so in question A, in determining the gene arrangement for these 3 linked genes, you just do the same thing that we've been doing, where you take the most progeny and you put that as the gene arrangement. And then B, you take the double crossovers and you get that, and then you switch them around until you find the correct one. And obviously I had a hard time switching around because I had so many different options and they all didn't work out. But then this one did work out. So we use the gene order was C, G, and then S plus, and then C plus, G plus, S. And then when you do the same thing that we've been doing with taking the top two and bottom one, and then bottom two, top one, then the top one, you get 27 for this one and 29, and then you add that to your value of 19 for the double crossover. But the thing that's unique about this one is that there were 0 of those offspring, so you do 0 plus 0 plus 19 for the double crossover over 1,000, and you get 1.9 map units, and then 7.5 map units for the other one. And then you'll multiply those two, 0.019 by 0.075, then you multiply that by 1,000, and you get 1.425, and then that's the expected, and you put that over the observed 19, you get 13.3%.
Okay, so number 4. So for A, we're just going to find the parental by finding the most common phenotypes, which is going to be BRF, and that's going to give us 379 offspring. And BR plus F plus is going to give us 385. So that's going to be our parental. The crossovers, which are the least phenotypes, which we find here. And that gives us 2 and 3. And so then, again, we switch, using the parental, we switch the first and second alleles, and then we switch the second and third alleles. And then we're able to find out that the arrangement is going to be the AN. So then we can take that to number C and use our cool little crossover thing. Use the first allele from the top with the bottom 2 and 3 alleles, and then the first allele from the bottom with the top 2 and 3. And then once we get all that, we find out that there are 98 AN plus, F plus, BR plus, 7 that are all 3 not wild type. Those to the number of double crossovers, we're able to see that 190 over 1,000, and when we multiply that by 100, we get 19 map units. Second part of C, we take the top 2 alleles and put it with the third allele on the bottom, and so we get 26 that are AN wild type, BR wild type, and 20 that are AN F wild type. So when we add that to the number of double crossovers, we get 51 over 1,000, and then that gives us 5.1 map units. The 2 map units together, before multiplying them by 100, we get 0.00969. And when we multiply that by the amount of offspring, which is 1,000, we get 6.69 expected. We put the 5 double crossovers that we observed over the 6.9 expected, and that gives us a 51.6% interference.
Okay, perfect. And then the last one, question number 5. So this is kind of a conceptual question. And so we're supposing that in all of these, the cell has the genotype dominant A, recessive A, dominant B, recessive B. In the first one, we're supposing that the homologous chromosomes, so they're not linked, they're on separate homologous chromosomes. In that case, it would produce 4 gametes, and each one of them would have a different allele in them, or a different gene, sorry. Or it would be A, so dominant A, recessive A, dominant B, recessive B. And the frequency would be 1/4 of those, because there's 4 of them, and so it would be a frequency of 25% for each. for B, we're supposing that dominant A is linked to dominant B, and recessive A is linked to recessive B. In this case, because they're on the same gene, they'll create two separate gametes, but there's no crossing over that occurs. And so 50% of them will be, 50% of them will have this genotype, and 50% of them will have this genotype because they're linked. They're on the same gene, and no crossing over takes place, so they stay there. In C, we're supposing that a crossover does take place between the A alleles and the B alleles. And so when that happens, 50% of the, because they're still linked, so just 50% of them will have this genotype and 50% will have this genotype. And then question D talks about the map units, the map distance between the A alleles and the B alleles. And so I drew this little picture. It has 7.8 map units between these alleles and 7.8 map units between these alleles. And our reasoning was just that if they were 50%, if it's over 50 map units apart, that means that they're not linked. And so the closer they are together, the least chance there is of crossing over taking place. And so if it was 50, there'd be 50% chance that these would occur. But because they're so close, we just said that it's 7.8% frequency of both the dominant A, recessive A, dominant B, recessive B alleles. And so, yeah, that's our video for you guys. Sorry if we went a little over, but there you have it.